So today I talk about the box-Ball system. So the result is not so recent, but it has classical aspects and quantum aspects and also probabilistic aspects. So I think this topic is a good fit to the program. So from my personal point of view, so there are, this is a brief chronicle of the development of the box-Ball system. The first example was discovered by Takahashi and Satsuma, or I should say they invented it just by intuition. And that was 1990. And soon after that, so-called ultradiscretization is found. So that shows a sort of classical integrability. And then shortly after that, in the end of the last century, so the connection to the crystal wave theory was found, and that provided the quantum integrability and quantum group theoretical generalizations. And after that, the connection to the Bethe ansatz, or actually the combinatorial version of the Bethe ansatz was found. And it led to the action angle variables and the KKR bijection, fermionic formulas, and solution of the initial value problem. In 2018, so randomized setting was introduced, and based on the thermodynamic Bethe ansatz for the generalized Gibbs ensemble, the limit shape of the consortium diagram was found. And furthermore, recently, so the general hydrodynamics was applied, and speed equation or velocity equation and the Riemann problem solved in certain setting. And also it led to the current fluctuations and large deviations. So I basically try to introduce these topics. So let me start the definition of the box-Ball system. Well, actually, like ASEP, there are N species version, and this is the 3 species version or 3 color version of the box-Ball system. So you imagine the array of infinitely many boxes where the distant boxes are all empty, which is denoted by 0. And each box can accommodate at most 1 ball, which can be colored by 1, 2, or 3. And here is one configuration of that system at time instant 0, for example. And t equal 1 and t equal 2 and so on. So that's a dynamical system, discrete, fully discrete. So what's the rule of the time evolution? So it consists of 3 steps concerning each color of the balls. So first you move ball 3, and then 2, and then 1. And what move I does is the following. So pick the leftmost ball with color I and move it to the nearest right empty box. And do the same for the other yet untouched color I balls. So how I can, let me show how this dynamics is reproduced. So we have a configuration like 3, 3, 2, and 1, 1. So leftmost ball move 3 is here. So this is going to be here. And then this is going to be here. And the move 3 is finished. And then move 2. Then I pick this, put it here. And then move 2 is finished. And then move 1 is like this and like this. So that's the reason why I'm going to get this time evolution. So you can easily see that the configuration consisting of the consecutive balls with this weakly decreasing color behaves solitons. It's stable. So if you, and this is your homework, but if you start from the random configuration like this, it doesn't propagate stably. It will be breakout. And moreover, in these solitons, you recognize that the velocity of the soliton is equal to its amplitude. In this example, 5 is a velocity. So somehow the bigger soliton is faster, like KDB solitons. So if you put 2 solitons together with different amplitudes, you can let them collide. So let's do that experiment that you can do on your desk. So this is an example of the collision of 2 solitons, amplitude 5 and 3. And this is a result of the application that move. And this is the result. And so here you observe rather remarkable things. So 2 solitons, they neither break apart nor stick together, but they come back exactly in the original amplitude 5 and 3. That's non-trivial. So amplitude of the individual soliton is conserved. And moreover, the soliton's amplitude are conserved, but the internal degrees of freedom has been exchanged like this. So it's analogous to the collision of hadron quarks, exchange of quarks in hadron collision. Moreover, there is a phase shift. So if you put the ruler to the trajectory of a soliton before and after the collision, you observe certain shift. That's a phase shift. So this presence of the phase shift is evidence that the theory is what system is essentially non-linear. If it's linear, just linear, it should be just X shape. But we have non-trivial phase shift. That's the evidence that the system is non-linear. So that's the two-body collisions. But then what about collision of three solitons? So here I have two examples for your comparison. So but both is I put the same content solitons, but with some somewhat different distance between them. So the order of the collision somehow a bit different in this example and this example. But you observe that the outgoing solitons contents are exactly the same. So that means the Yang-Baxter relation is valid. So solitons in final states are independent of the order of the collisions. So that's really indicate that this system is integrable. And where this integrity comes from, that's an important question.
So in this example, you have a 3-1 and 2.
3-1 and
In the bottom, you have 3 and 2-1.
3 and 2-1. Yeah, but so it's due to the exchange of the internal degrees of freedom.
So they do exchange it.
So this hasn't been, this is, original, but partially exchanged. Yeah. So actually, there is a double origin of integrability, classical and quantum. So first, classical integrability. So that's the ultradiscretization that I mentioned before of soliton equation. So the key formula is very simple. Identity where A and B is assumed to be real. And then, so this is just elementary exercise or a low temperature limit. Well, anyway, so it means the following. So this is a replacement of the two binary operation, addition and multiplication by max and addition, like this. The good thing about this replacement is that it keeps the distributive law. So if you apply this replacement to the left-hand side, you get this. And right-hand side, you get this. And this it remains equal. So this is so-called tropical variable change in mathematics literature. But the soliton people named it as ultradiscretization. Anyway, so it was found, the following was found. So ultradiscretization of a discrete KdV equation gives an evolution equation of the single color box-Ball system in the middle of 90s by Satsuma and his collaborators. So that explained one classical integrality of the system. And what about quantum? So it's a solvable lattice model at temperature 0. So here is, again, example of two soliton collision time evolution pattern. But it emerges from a configuration of the 2D lattice model in statistical mechanics of this form by forgetting the hidden variable on the horizontal edge called carrier. So this is really two-dimensional vertex model, and where you have the physical degrees of freedom also on the horizontal edge. But if you forget about that, then you are only left with variables on the horizontal vertical edges, and that exactly gives you this configuration.
There is some rules.
Pardon?
There is some rules to fill.
Rules.
Rules. How you choose the hidden variable?
How I choose this? Yeah, I'm going to explain. Thank you. So the n-color box-Ball system is nothing but a 2D solvable vertex model associated with quantum group UQSLn+1 hat at Q equals 0. So Q plays the role of temperature. And the low transfer matrix at Q equals 0 becomes the deterministic map, which is defined by the unique configuration surviving at Q equals 0. That probably answers your question. And the time evolution, that is the time evolution of the box-Ball system. And maybe you wonder why we have 2 digits here. So that's because I am taking the degree 2 symmetric tensor representation as the auxiliary space of the transfer matrix. So in principle, you can choose any degrees of transfer matrix to define the commuting family of time evolution for the box-Born system. So I said that we first introduce 2D solvable vertex model and then take Q equals 0 limit. That's a bit cumbersome, but you can start from the beginning, the Q0 setting. That is possible by use of the so-called crystal-based theory. So this is the theory of quantum group at Q equals 0. So from the beginning, you may formulate the system by using this thing. So in this formulation, what is the local dynamic? So I said that this dynamical law, this is quite non-local. You have to look for the nearest like empty box, which is non-local and not so very good, although it's quite intuitive. But once you introduce this hidden variable, it becomes completely local. So the problem is just to determine this vertex weights. So that is the
representation.
Pardon?
If you choose different representation on the horizontal line,
horizontal and vertical can be chosen differently.
you will have a different induced dynamic.
So that does correspond to this type. Yeah, depending on the degrees of the. So maybe you have vector representation, but you may have anti-symmetric tensor representation, and then you take Q0 limit, and then you obtain the dynamic steel box-Born system.
But then the dynamic depends on lambda.
Can depend on what?
On the choice.
Even this one. That is degrees of horizontal, the auxiliary space. Yeah, but they are all commuting and somewhat different. So the original dynamics that I explained in terms of ball moving algorithm correspond to T infinity, which is the simplest case. Yeah. Actually, T1 is just a translation. So I said that everything becomes local by introducing this carrier degrees of freedom, and that is so that is the interaction of carrier and local balls, the pick up and down rule of balls, and that is called so-called combinatorial R, which is a quantum R matrix at Q equals 0. So this is a very kind of ultimate limit of the quantum R matrix, where the matrix element becomes 0 or 1, and it becomes certain permutation matrix. So I just omit the matrix, but combinatorial R. But anyway, it's a kind of bijection between from the pair of semi-standard Young Tarot to the another pair of semi-standard Young Tarot, still satisfying Yang-Baxter equation. So once you understand such quantum origin of the box-Born system, you can play a lot of generalization and game. For example, this crystal can be formulated for other types, not type A and so on. So what sort of things come out from that? So here is some example. So there exists an integral cellular automaton with quantum group symmetry. For example, we can take fine real D15 a certain hat automaton, which looks like this for the two-body scattering. So here you see that initially we had, here we have bar letters, not just balls. So we should understand it really as a particle, anti-particle system with bar letters. So here you see that in the initial configuration, we have 2 and 2 bar degrees of freedom, but it's absent here. But instead, it has been replaced by 3 and 3 bar here. So the particles and antiparticles undergo pair creation and annihilation. And the N-color box-Born system, which corresponds to the type A, is nothing but the antiparticle free sector of this automaton. And it's a fundamental problem that what is the degrees of soliton in such system, and what is the scattering rule of 2 solitons, including their phase shift? That's a fundamental question, but it can be neatly described by, again, by this combinatorial by such rule. So I'm not going to explain this, but anyway, so combinatorial R has certain affinization, and this affinization part controls the phase shift. Anyway, so it really description by combinatorial really fit this sort of generalization. Yeah.
Yeah. So you consider affine algebra, but you can also, there is no general Lorentzian Casimir algebra. What do you get?
Well, I have never tried, yeah, and I'm not sure if there are any such good bases like this. Yeah, but
you know the system, if you try to define the system on Lorentzian Casimir algebra, maybe you will solve it's integrable because it's special, but actually it's a chaotic system.
I see.
Yeah, is it chaotic?
Yeah, well, I have no idea. Yeah, but yeah, that's an interesting direction to pursue. Yeah. Any other questions? Okay. So that's one sort of generalization. And another generalization maybe is you can introduce a box-ball system with reflecting end. So here is a reflecting on the right. So although in this system, it looks a bit messy, but we have to design the system so that it accommodates not only right-going soliton, but left-going soliton after the boundary reflection. So there it's possible to certainly set up so-called combinatorial K matrix and let soliton reflect at the boundary, still satisfying this reflection equation that I talked in my second block. So here you see that two solitons may be, well, this soliton reflected and then collide and so on, so something like that. But anyway, so that sort of generalization also possible. But anyway, so we now understand that the box-ball system, which is a cellular automaton, has double origin of integrability. The classical origin is its equation motion is understood as or identified as a ultradiscretization or tropicalization of certain soliton equation. That's one way of understanding its integrability. And another way of understanding is Q0 limit of the quantum integral system, where the R matrix must be computed along the proper basis, and that corresponds to the crystal base. Yeah. So that's the two origin. Now let's remember what is the most marvelous approach or method of solving these systems. So here we have initial value problem, and it is solved by so-called inverse scattering method. And Bethe ansatz is supposed to be a quantization of it. So most typically algebraic Bethe ansatz is a sort of, yeah, it's sometimes often called quantum inverse scattering method. So it is natural to expect that there should be something here, method here to solve or analyze this ultra-discrete integral system. And that's turned out to be provided by so-called KKR bijection. So the Kirov-Kirillov-Reshetkin bijection introduced in middle 80s. It was introduced for very different purpose because you see it was middle 80s, but box-ball system, first example came 1990. So it was before the introduction of a box-ball system. So for what it was invented? So it asserts the formal completeness of the hypothetical string solutions to the Bethe equation at the combinatorial level. It leads to a fermionic formula for Kostoka polynomials and their generalizations. So for the simplest spin 1/2 case with Q equal 1 dates back to Bethe himself. So this Q equal 1 case, Kostoka polynomial becomes Kostoka number, which is the number of so-called Dick-Fass. And Bethe came up with certain formula, which I'm going to show in a moment, and try to prove that. And it was well, much generalized by this KKR bijection, and that's all things. So that was the original reason that this map KKR bijection was introduced. But its remarkable connection to BBS was discovered in the beginning of this century. So according to that, the quasi-particles consisting of the fermionic formula is nothing but the BBS soliton. So I'm going to explain about this. So let's come back to the 1931 problem. So that's a spin 1/2 periodic Heisenberg chain with Hamiltonian, this form. And suppose we consider length 6 chain and 3 down, 3 up spin sectors. Then Bethe ansatz goes as follows. So you try to solve this Bethe equation. And once you found the solution, then you know that eigenvalue and eigenvector. That's the Bethe ansatz. But of course, there are many eigenvectors and eigenvalues. So it matters how many solutions you get to the Bethe equation. So in this case, the Kostaka number is 5. So you should get 5 solutions, physically allowed solutions. And here it is. So this is a plot of U1, U2, U3 on the complex U plane, but 90 degrees rotated. So this is a vertical alone is actually a real axis. And there are 5 solutions. So here you observe, so it comes with certain pattern, which I call string, or which people call strings. So what are strings? Strings are nearly 2i equidistant configuration, symmetric with respect to real axis. So this is correspond to the length 3 string sitting on the real, origin. And here length 1 string on the real axis, but there are 3 of them. Here length 2 string and length 1 string. Now, the invention of Kirov was to attach such combinatorial object to visualize such patterns, string solution patterns. So of course, you know you immediately know what the meaning of this Young diagram. So this means there is a string of length 3 string, and there are 1 string, and there are 3 of them, and 2 string and 1 string. But the point is not only the Young diagram, but you need to assign certain number, which I call leading. So this number specifies the relative position of the strings. So for example, if you look at these 3 patterns, so the relative position of 2 string and 1 string is different. And that is distinguished by these integers assigned to each row. So this red object is what is called Licht configuration. And it forms the one side of the KKR projection. And what about the other side? Well, before showing that, you should recognize that this red object, Licht configuration, is a combinatorial analog of the Bethe roots or string solutions. The other side of the bijection is combinatorial analog of the Bethe states. So that's spin up or down states, but because we are in a combinatorics, there should be no superposition, just 1 or 0 or 1. And 0, 1, 3 of 1, and 3 of 0. Yeah. And this is an image of the bijection.
So this is the same coding than just this picture.
Yeah, it's quite similar that I haven't identified the precise relation. Yeah. Yeah, maybe we can discuss. It's very interesting. Yeah, I'm going to explain how this bijection goes. But anyway, so let me repeat. So red part is a Licht configuration, which corresponds to the combinatorial analog of the Bethe roots or string solutions. And the green one is a combinatorial analog of Bethe states, which again is monomial because we are in a combinatorial situation. So I call it as combinatorial Bethe ansatz. Anyway, let's jump up to the n plus 1 situation. So the KKR bijection is a 1-to-1 correspondence between highest states and Licht configuration. And typically for n equals 3 case, it looks like this. So let me explain both sides. The left-hand side, this is the highest states. What does it mean? So highest states is what consists of 0 to n, satisfying a so-called highest condition. So this is really the Dick path condition for n if n is 1. So if you look at the subword of the left part, then the number of 0 is not less than number 1 and 2 and so on. So for n is 1, that means we never go below the sea level or something like that. And for higher n, maybe if you know the weight lattice, then you stay in the positive chamber of weight lattice, that sort of things. So that is the highest states, and that's the analog of Bethe vectors. And here it's a Ligt configuration for higher rank or SLN plus 1. So it consists of two parts, red parts and blue parts. The red part is called configuration, and it is an n-tuple of Young diagrams. And blue part is called leading, and it is integers assigned to each row. And altogether, it's called Ligt configuration. But you have some selection, non-trivial selection rule between this configuration and the leading, which I'm going to explain on the next page. So here is a part of the Ligt configuration. So I pick up, for example, mu2 or something like that. So I look at, let's look at mu A. And suppose that the length of the how to say, with this I row, there are not MAI of such row in this Young diagram. And you should assign certain leading to this cliff. And the selection rule is it must be between 0 and certain upper bound, HAI. And this upper bound is given by this formula, where L is the length of the spin chain, and C is the Carter matrix of SLN plus 1. So good thing about, well, yeah, I think this is constraint is non-trivial because why? So you must have HAI positive or non-negative in order to have this, satisfy this condition. And that is a non-trivial constraint among the shape of the diagram. Otherwise, it is very, how to say, easy to calculate the number of Ligt configuration for a given prescribed configuration. It's just given by this formula because of this constraint. Well, I should also mention that I'm going to call it as a vacancy, the holes. This is a kind of Bethe ansatz or TBA terminology. So this is a product of the binomials. And this is the SLM plus 1 generalization of Bethe's formula for the number of string solutions, which is the so-called Fermi character formula for KR modules. But anyway, so let's look at Bethe's paper. So here you see the product of binomials with this capital Q is given by system size minus twice minimum of T and N in D. So it's really is a generalization. Well, this is a really generalization of Bethe's formula to SLN plus 1. So now I should also explain how the KKR bijection is constructed, KKR algorithm. So because bijection, we have two directions, but let me just explain one direction. So given Ligt configuration like this, how to find its image? Namely, the highest path from that. So this is a one-page explanation along my example. So given Ligt configuration, where this leftmost part is I just put for convenience. So really this part is matters, but this means that the system size is 8. Anyway, so given the Ligt configurations, the algorithm tells you that there are boxes that you can remove or you should remove. These boxes are denoted by blue. So you will remove it with its digging as well. But the algorithm is designed so that after the removal, it still is a Ligt configuration, which is non-trivial, because I said that the constraints of the rigging at this vacancy is somewhat non-trivial. But anyway, so it is designed so that after removal, you also obtain a Ligt configuration again. So you can repeat this removal procedure until you end up with empty Ligt configuration. So every time you remove boxes, you record the number of box -1 to on its own, like this red letters. So I have removed 2 boxes, so I recorded 1, and I removed 3 boxes, and I put 2 here, and so on. Here I just removed 1, 0, 1. So reading these red letters backwards, you obtain the image. So it's quite nested, inductive, messy algorithm, and it's very easy to make mistake if you do it by your hand. but it's mathematically perfectly well-defined algorithm, and you can program it on your computer, and program gives you the image almost instantly for any highest states of length, let's say 100, something like that. Anyway, so we have now known that there is a bijection between highest states and Licht configuration. So now it's time to observe the dynamics of the box-ball system via KKR bijection. So all these passes are, states are highest states. So each time you can trace the time evolution in terms of the Licht configurations. Can you guess what sort of Licht configuration we are getting? Like this. So the answer is like this. So that means configuration, namely this Young diagram part, is not changed. They are conserved quantities or action variable. Rigging flows linearly, which means that that's an action variable, angle variable. And since we have a way to go such data and back, so the KKR bijection operates linearize the dynamics, and it serves as a direct and inverse scattering map. In short, the Licht configuration is nothing but the action angle variable box-ball system. Especially mu1 Young diagram is nothing but the list of the amplitude of the solitons. Yeah, amplitude 4, 3, 2 solitons, it's here. And actually it has a velocity 4, 3, 2 equal to the amplitude. So the rigging or velocity vector in the sense of rigging actually coincides with the velocity vector in the real space. So but by now, I think it's almost clear that now the Bethe string, or combinatorial version, and soliton in BBS is in one-to-one correspondence. So I think this sort of correspondence, soliton string correspondence. So physically, BBS soliton is the bound state of magnons in a combinatorial setting. And this configuration part of the data of the Licht configuration will be referred to as a soliton content. Now let's come to the probabilistic setting or randomized box-ball system. So we have box-ball system states here, and by taking the KKR map, we obtain the soliton content and the probo Young diagram. Now, let's randomize those BBS states by introducing, let's say, IID measure on the set of states. Well, this IID measure, for example, can be parameterized by P0 to Pn because we have local states 0 to n. And then ask the following problem. So determine the scaling form of the most probable configuration in the limits of when the system size goes to infinity. So this can be done by TBA. So from now on, I think the argument is not rigorous because I'm relying on TBA. But anyway, this can be done by TBA by minimizing the free energy F associated with this. So here is a Bethe's factor product of binomials. And this fugacity factor represents this IID measure like this. So the IID measure at the level of BA-base that's induce the measure on the nth probable Young diagram. Right? I'm going to determine the most probable one. So, and let's assume the linear scaling of the number of the strings of color A and length I, and whole of color I and length I, like this. Scaled, those quantities are lower than sigmas. And this is the definition of the vacancy in the scaled variables. And I assumed this region where Pi is here. Now the most probable configuration, or how to say, shape is determined by taking this free energy minimum condition, and that leads to the TBA equation. And this factor can be taken into account as the limiting behavior of these Y variables. like this. So by the way, this notation Y is probably due to going back to, well, notation is not notation, but the names due for Xi and Yang, I think, who firstly introduced the TVA in late 60s. So usually it is denoted by exponential minus beta Schrödinger energy or something like that, but I just draw it as a Y. But anyway, taking the exponential of both sides, we get the so-called constant Y system, which has something to do also with cluster algebras. But in this context, I don't see any reason to assume that they live on the quantum torus and Q commuting. It's just the usual numbers. But it has got many interesting periodicity properties, that's all things. But yeah, let's not talk about that. Anyway, so we can solve it, or we can find a solution to that. So it's expressed by this form where QAI is actually just Schur function. Sorry for about this strange notation. So Schur function for this Young diagram. So depth A and width I, rectangular Young diagram, you have Schur function, and variable PA is just the IID parameter in the previous page here. And using that, so the limit shape of the soliton content is given by this formula where, so this red thing is drawn here. So we are considering the A part of the configuration, and so it's the ith column of mu A, the scale by 1 over L system size, it becomes like this. And also the width of the Young diagram scales as a log L. Well, if these PAs and PN are strictly unequal, if they are going to collide, then it is going to be critical and very subtle and probably very interesting, but we haven't studied it seriously. So that's for general P variables, but if we specialize P's in this manner, in terms of single variable Q, then yeah, these formulas is considerably simplified in this manner, like this. So not only this eta AI, but we can give an explicit formula for the strings density and the whole density like this. So here, this is experiment comparison with the experiment. So the two-color BBS with 1,000 sites with these IID parameters, and vertically 1 over L scaled soliton contents is this, where blue lines, a broad plot is just experiment. I really generated such samples and computed the soliton content or configuration. And the orange line is a kind of a theoretical curve by TVA. So agreement is more or less good. So that's a sort of limit shape problem. Actually, I think maybe it's interesting or may not, I don't know, to investigate the fluctuation of these Young diagrams. I think nobody has ever investigated that.
These are particular states that you consider. They are stationary states of your dynamics, right?
Yeah, no dynamical elements is here. Yeah, just.
But they don't cover the full set of GGEs, particular set of GGEs.
Yeah, not full set. Well, because I assume that IID. IID means we have kind of very strict relation among the GG temperatures.
Yes.
Yeah.
You know how to construct more general.
Well, that I will touch in the next few pages. So, for example, so this betas must be related to this IID parameter in that manner. So, in that case, it's not fully general GG. So, this is my final topic. Maybe I'll finish 10 minutes early. So, from here, I just consider single color BBS. And this analysis, maybe I'm going to talk from now on, is I done with Gregor, with Rich, and Vance and Pastier. And yeah, I enjoyed visiting them in Saclay a few times. Anyway, so yeah, here, so we can do slightly bit more. So we can control two densities. The one is a ball density, and that's already present in the IID, but we can also control the soliton density. So, the solitons are collective mode of the balls, and many balls consist of one soliton. So soliton is few, there are fewer solitons than number of balls, and those are controlled by A and Z. And the IID situation is, specialization. Anyway, so in that generalized GG context, or two temperature GG, so we can slightly generalize the result in the previous page. So this is for SLN, but the N is one case, and the slight generalization of these formula is like this. Yeah. And so there is a speed equation or effective speed equation. What is the notation of this VLJ? So as I said, there is a time evolution, commuting time evolution labeled by index L. So that corresponds to the capacity of the carrier. So I'm considering the dynamics under TL. That's the superscript L. Yeah. And J is amplitude J soliton. So VLJ is effective velocity of amplitude J soliton under this dynamics TL. Yeah. And this structure of equation, now we've seen it in Amor's talk last week as well. But you see that this is our phase shift formula for the single species box-ball system. And this is the density of the case soliton. So that's a speed equation. And well, it's natural to write the equation in that manner, but the rigorous derivation sort of justified by people like Croydon-san, Sasada-san, and so on. Anyway, we take it as okay, and we try to find a solution fitting these TBA result. And the result is like this. So curiously, it has very simple formula, or kind of intrinsic formula using the whole densities like this. And anyway, this summation can also be taken explicitly, and we end up some elementary function results. And anyway, using these results, we can, for example, compute the stationary ball current under time evolution TL. And so because one amplitude K soliton carries K balls, so K times rho K times velocity, and we get this formula. Anyway, that's TBL result. And from now on, I further specialize to this station, A, Z equal Q. So now, based on such formula, we can also study the dynamical problem. Most probable popular setting is the so-called Riemann problem. So the Riemann problem describes the profile of the fluid, starting from the homogeneous initial condition, except one discontinuity. So in our case, we consider the BBS with initial at the time t equals 0. There is some soliton gas confined in the left side of the system, and here it's empty. You can prepare such state on the computer. And then we remove the wall, and then what happens? Can you imagine? What's the density profile? Maybe you have good guess. So it's written here. So we have density plateau. And why? Can you guess why it is so? So it's pretty simple. So let's consider the amplitude of the contributing solitons for each plateaus. So for here, so all the solitons can contribute, but here it's somewhat distant from the wall. So the slowest soliton, which is amplitude 1 soliton, hasn't still reached this region. So that means a drop of the density to some amount. And here it's furthermore apart. So the amplitude 1 and 2 solitons are too slow to reach this region, and so on. So every time you proceed to the right, then you miss the slower solitons contributing to the densities. So that's the reason why we get the density plateau like this. Now, plateaus grow linearly and horizontally in time t, obviously. So the plot against the ratio R over T, let's call it zeta collapse into a single curve, at least when R and TR gets large. So let's imagine such picture is drawn like this, and call the edge of the case plateau, the position of a case plateau as zeta k, and density or height of the case plateau is hk. So the basic problem is to determine these hk and zeta k in terms of this density p. That's sort of the very typical problem in the Riemann problem. And that is a there is a GHD prediction. So according to GHD, so we obtain such result where P, density P is parameterized in this manner. And let's compare the result with experiment or simulation. So this is a simulation with 50,000 samples and plot against zeta and density. And initial density in the reservoir is 0.4. And time step is 500. So this orange plot is the simulation result. And we really indeed observe that density plateau. This dot are the theoretical prediction by GHD. So the agreement is rather good. But actually plateau edges are not strict and exhibit some broadening. And this is maybe that they're so very expert in this audience. I'm a bit hesitant. This is due to the diffuse correction to the ballistic picture, which may be viewed as a finite effect. So let's try to give the analytical description of the diffusive broadening of the plateau edges. So this is a plateau edge. So if we plot the edge in terms of this zeta variable, then it becomes sharper and sharper with respect to time and with some such factor. So for general grounds, we assume that this profile can be expressed as the interpolation of two stable plateau functions here. So that means this error function becomes 0 when u is infinite, and 2 if u becomes minus infinite. So that means if R is, if we look at far distant R, then I think this kills and we get, no, this becomes 0 and we are left with this factor describing this part. And if R is minus infinite, I think this becomes 2 and this is cancelled and we get this one as this. And so it should be interpolated by this error function. But the essential factor is here, which corresponds to the diffusion constant. Now we have 3 integer indices, J, L, and K. So let me recall what are they. So J, we are looking at the density of the J's amplitude, J sort. And L and K. So K specify the position of the plateau. So there are many plateaus, the plateau 1, 2, 3, and so on. So we are looking at the vicinity of the case plateau. That's K. And L is again this time evolution TL. So we are considering the time evolution TL. So this diffusion constant should be obtained theoretically. And I followed the GHD papers, well, maybe Vincent and Gregoire, and yeah. And this we got as a conjecture. So maybe we tried hard enough to prove it, but yeah, for numerical, well, for algebraic manipulation, we got this conjecture. So this is a GHD Bethe result, like this. So if we plug this result into here and plot this profile against this variable, that should collapse into single curve, and that's it. So yeah, so GHD is really working, and so that's our result. Anyway, so maybe I should probably close with some comments. Well, additional result. So the equation motion, I didn't tell much about that, but the equation motion of BBS is kind of bilinearized in terms of how functions. So bilinearized quotation mark because it's UD sense, tropical sense. So usually Hirota bilinear equation takes this is the most typical Hirota equation, but we have to take the piecewise linear tropical or UD limit, and then it should become this form. So I replace the multiplication by plus and addition by max. So it's really is expressed in this manner. But what is this tau for BBS? So it is an UD analog of Hirota tau function, and it again is the sort of corner transform matrix, again quotation mark. So I probably will not explain this talk, but if you are interested, maybe we can talk personally after later. Yeah. But anyway, using this result, we can write down the explicit piecewise linear formula for the KKR map. So I explained this KKR bijection, very nasty algorithm of inductive, but it can be expressed in a single line using this Hirota-like piecewise linear tau function. So that's one result. And if you impose periodic boundary condition to the BBS, things become even more intriguing. So the periodic boundary condition BBS dynamics is invertible. So that means you can come back to exactly the original configuration after certain time step, which I call fundamental cycle M. But in the quantum integral interpretation, this time evolution is a multiplication of a transfer matrix. So if I compute the Bethe eigenvalue of the properly normalized transfer matrix and set Q equals 0, it turns out that this fundamental cycle exactly satisfies this condition. So this is very kind of gratifying agreement with the quantum integrality interpretation. So Bethe eigenvalue with proper normalization and Q equals 0, and string content has been chosen so that the solitons in the BBS states exactly satisfy this fundamental cycle condition. That's one thing. And the solution of the initial value problem for the periodic box-ball system is expressed in this manner, where theta becomes a tropical Riemann theta function. Yeah, I forgot to say one thing. Cannot remember. But anyway, so this tropical Riemann theta function is a sort of limit of this tau function. Such example exists. Sorry. Yeah, maybe what I once, one thing I forgot to mention is, here. So this observation effectively solves the initial value problem of the BBS. So given BBS states 0, 1, 3, you may be asked, find the state after 1,000 time steps. But dynamics is nonlinear at the level of BBS. So what you do is you make the KKR map to the Richter configuration of the initial state. And then time evolution is just the addition of the velocity vector. It becomes straight motion. And then you get another Richter configuration, and then you apply inverse KKR map. And that leads to the solution. Yeah.
So, for integrable system, usually they become linear motion in the Jacobian of the Riemann spectral curve.
Yeah.
Does it mean that this parametrization with Young tableau is somewhere the tropical analog of the Jacobian?
Exactly. Right. But this is for infinite system. But I was just telling about the periodic situation. Exactly such corresponds false. So you can introduce certain identification. So you have to make things compact. So not just leading runs not only from minus infinity but plus infinity, but you introduce certain modular conditions.
So there is an analog of that divisor? Or...
Yes, some sort of, yeah. And so this result is the outcome of such, yeah. So I think I should stop here.